Okay, we're good. Today we're fortunate to have Professor Marcia Rieke. Her area is infrared sky observation. She specializes in large format infrared focal planes. She went to MIT, got her doctorate at MIT. She was a deputy PI on the NICMOS, which is the near infrared camera multiple object spectrometer for the Hubble telescope. She's the PI of Nearcam, which is part of the James Webb Telescope. So with her, we're very lucky to get her as our colloquium speaker. I will say one other thing. She's a member of the National Academy also, so, which is, as you guys know, that's huge. So,
Thank you. I think, it's on. So I have to tell you that I should make a list someday of all of the optical sciences alums that help make this telescope work, because it's a big number. And so without the people that came from this college, the telescope would have been in much worse shape. So let me give you a sense of what we did, what I spent the last 24 years of my life worrying about, and why we're having so much fun now. So this is one of the, what we call early release observations. It was taken basically for combined PR and science interest. And the way this image is produced, it was taken at a series of wavelengths through Nearcam. And these designations like F200W means a 2.0 micron wide filter, sort of lambda over delta lambda of about 4. And there was a whole series of these, and that you can see the color coding, which is partly monotonic with wavelength, but not entirely, because some of the idea here is to colorize the picture, because of course these are all infrared wavelengths, so there's no, your eye wouldn't see anything. And so the colors are chosen to achieve two goals. One goal is to make it, highlight some interesting science aspect, and the other is to make it artistic and visually appealing. And so you can see the visually appealing part in that the upper part of the picture looks like blue sky, and that's basically a region that does not have very much interstellar dust, interstellar material. And the bottom part has got lots of dust, very large molecules, polyaromatic hydrocarbons, which comes through in this one particular filter. And you may be able to see a little yellow spot here. That's where there's a shock front, and the filter that isolates that is sensitive to some lines from molecular hydrogen. So this is meant to be pretty, but also meant to pick out some things that will be interesting to an astronomer. Okay, so we launched Christmas morning. It was like 5:20 a.m. here, so you had to kind of get up before the presents were unwrapped. And it was an absolutely perfect launch. The launch was from Kourou in French Guiana, because the European Space Agency provided the rocket. That was their major contribution to the mission. And the Arianespace engineers hit it so perfectly that we didn't have to use very much of the onboard fuel to get to the L2 orbit. And so, the mission had a goal of had a requirement of a 5-year lifetime and a 10-year goal. But we have enough residual fuel for station keeping, because I'll explain, the orbit here is at a place called the second Lagrange point, which is semi-stable, which means you do have to do what we call station keeping, fire the rockets every couple months to keep in that spot. And we have enough such fuel to go for like 25 years. Now, whether the cryogenic mechanisms will last that long, that's another question, but at least we won't run out of fuel. And the launch, of course, is always a scary time because the rocket's a controlled explosion, but this mission had many other bits of worrisome things, because As I'll show you, it had to be folded up to fit in the rocket nose cone, and so it had to unfold, and not just the telescope part had to unfold, but this sun shield that's used to keep it cold had to unfold. And the sun shield was the source of most of the 300-odd single-point failures, because there were straps that held down the mylar material so that it wouldn't shuck around during launch and get tangled up. And getting this unfolded completely took over 10 days, and those were, people were nervous, but it went perfectly, and it went perfectly, I think, because we'd practiced so many times and found all the ways it could screw up. So, okay, and of course, out here, this L2 point, we're 4 times further away from the Earth than the Moon, so servicing is not possible. No, we don't have a capability to go there. So why do we put so much emphasis on having a big sun shield? That sun shield is almost as big as a tennis court. And that's because if we want to go after really distant, faint sources at infrared wavelengths, we have to get rid of the heat from the surroundings. So I've done 10-micron observations from telescopes up on Mount Lemmon. It is hard work. That's not a great way to earn a living, but we did that in the 70s and 80s because there wasn't a choice. But it's so much easier to go to space where, you can see this man here, and it's very hard to tell. He's holding a match. And against this bright background, which is akin to how you observe on the ground at 10 microns, if you get rid of that, bingo, it's easy to see the match. And that's the whole point of one of the points of going into space. I mean, there are bands where the Earth's atmosphere is transparent, but being able to have a cold telescope is just critical to what we wanted to do. So this gives you an overall view of the mission. You can see this sun shield with 5 layers. So the sunward facing side is at something like 350 degrees Kelvin, and the telescope is down around 40 degrees Kelvin. So it is a very efficient sun shield. It's doing a great job of rejecting the heat. And you can also see that the primary mirror is segmented, 18 segments. And each of those segments is fully adjustable in 6 degrees of freedom, and it can also be adjusted slightly in radius of curvature. Not a lot, but you can do a little bit to tweak things up. And most of the cooling here is passive. The mid-infrared instrument has arsenic-doped silicon detectors that have to run at 7 Kelvin, and so there is a small cryocooler just for those detectors. And the rest of the instrument package is cooled passively. And the instrument package is very ambitious and complicated. There's both imaging and spectroscopy, and some of the spectroscopy is quite remarkable because it uses the first multi-object spectroscopy in space, where it's almost like a Rube Goldberg device made out of silicon that has a whole spate of slits, and you can run a magnet across the top of this device and have selected the slits you want open electrically, and bingo, you can match the slits to the objects you want to get spectra of, and it's fully programmable from the ground. And it's amazing. It's also amazingly hard to plan your observation because you have to have had high quality imaging ahead of time to know where to put, which slits to open up. But I can tell you, having seen some of the results, getting spectra of 100 galaxies at higher redshifts than have ever had their spectra taken before, it's worth it, even though it's complicated. Okay, so for those of you that like telescope optical paths, this gives you a little bit of a layout of what JWST looks like. And the focal length is enormous because it's basically an F20 system, and that was originally chosen when we were going to potentially use indium antimonide detectors, and that would match the size, the pixel scale of the indium antimonide detectors. And you can tell that the people that were doing the very early work on this didn't understand that people making infrared instruments always have pupil stops and re-imaging optics, and you don't have to have it match exactly. But that's where the F20 came from. Being a three-mirror anastigmat is a very convenient design. This fine steering mirror is at a pupil, and that is run off an error signal generated by a fine guidance sensor in the focal plane that tracks a star outside the science field of view and makes certain that any of the little bits of jitter or thermal issues that might affect the pointing are taken out. And the jitter that we've observed after we've done this fine guiding is less than a milliarc second over an hour time scale. Really, really great. As you'll see, Nearcam has a pupil imaging lens, and this gives you a sense of what the pupil looks like. So the instrument suite, we have a shared focal plane, and in fact, we can run two instruments simultaneously. The biggest single limitation there actually is the data rate to the ground. People call me the pixel pig with Nearcam because we have 40 megapixels, which of course doesn't sound like very much for a camera anymore, but for a camera at L2 running at 40 Kelvin, it's not too bad. But Nearcam can overflow the telemetry system, and in fact we have various co-adding schemes so we don't do that. But it is possible to run Nearcam with one of the other instruments and get two sets of data at once. And for some of the deep survey work looking for the most distant galaxies, that's a really nice feature because you're doubling the utility of your telescope. And you can see a little bit about the characteristics. One of the things that's most powerful on Webb in many ways is that it has so much spectroscopy. Much better spectroscopy than one ever had with Hubble or with the Spitzer Space Telescope. And if you look at the proposal pressure, it was strongest for the spectroscopic instruments, followed closely by Nearcam. But okay, so let me just show you a little bit about what Nearcam looks like. And because Nearcam is also the wavefront sensor, that is, we took all the imagery used to align the telescope. We take the images that are used to keep the mirror segments aligned. It needed to be fully redundant, meaning that if something jammed, there was a whole nother one that you could use. So this shows you half of Nearcam. The other half is a mirror image, and they're bolted together back to back. And this is great for science because we then have two adjacent fields of view that double the rate at which you can do a deep survey. So this was very nice. It also meant that Nearcam had to have exquisite optical performance. And you can see the light comes in, and we have a dichroic, so we have a short wavelength arm and a long wavelength arm, and this split allowed us to match the pixel scale to the wavelength, to, not precisely, but Nearcam is diffraction limited. Well, it's actually diffraction limited now at a micron because the telescope worked better, but it samples the diffraction limited image correctly at 2 microns and 4 microns. So we were able to take advantage of this split. The split had a number of other engineering advantages, like Lockheed Martin, who is our prime contractor for Nearcam, made a mistake when they put out the first RFP for our bandpass filters. And they were thinking of our long wavelength detectors, which can work from about 0.5 microns through 5 microns. And Lockheed wrote down that you had to be any one bandpass filter had to be totally blocked outside the filter bandpass. And that's really hard to achieve with normal coatings and normal substrates. But by having this split so that the long wavelength arm doesn't have to be used any shorter than 2.4 microns, you could change the blocking requirements by taking advantage. And the short wavelength focal planes, those detectors cut off at 2.5 microns, and so they don't need to be blocked at the long wavelengths. And once you went back and put the correct blocking requirements in, then people were happy to bid on the filters. But initially, no one bid, and it was like, okay, I know why they didn't bid, because you put impossible requirements in. Nearcam also has a coronagraphic capability. This focus and alignment mechanism was mostly used to ensure that the Nearcam pupil was matched exactly to the telescope pupil, and I'll show another picture that explains why that was so important. And this just shows you what half of it looks like in real life. Unfortunately, it's mostly covered by baffles, so it's not so interesting to actually see. And in terms of physical dimensions, this distance here is about 4 feet, and the whole cryogenic part of Nearcam weighs about 150 kilograms, so it's pretty dense. Oops, we skipped one there. My changer is not working so well. So there were some questions about why it was good to have a science instrument be the wavefront sensor that basically saved an instrument volume in the focal in the instrument package, which is always a good thing, and save some mass and power. And one of the things that being the wavefront sensor meant that Nearcam had to be nearly perfect optically itself. And the reason is that if you take images through Nearcam and use those to align the telescope, those images will also null out the Nearcam errors, but then when you go observe with another instrument, those errors would be present to them because we imprinted them into the telescope alignment. And so when you go through the numbers, the goal was to have the telescope diffraction limited at 2.12 microns, so using your old rule of thumb, that meant we had to be somewhere in the neighborhood of 151 nanometers wavefront error. And Nearcam's part of the pie was only 72. And that's not, in an absolute number, it might be a little bit hard to think about, but when you think about the fact that this was figured and built and assembled at room temperature, cooled down to 40 Kelvin, and also subjected to the vibration of launch, and it still had that same value, that took some engineering. And Lockheed came up with a very clever scheme of how it was basically an elaborate spreadsheet that took where you wanted to end up at 40 Kelvin, and then used a series of calculations taking into account all the materials properties, like how does the refractive index of the lens materials change between room temperature and 40 Kelvin, and how do all the mechanical elements move. And they predicted exactly where to put the lenses at room temperature to be correct at 40 Kelvin, and we only had to align Nearcam once, and I found that to be pretty darn remarkable given the requirements and how much had to be done. So one of the driving parameters for Nearcam was to do deep surveys, and I can attest that we got our first deep survey data just a month ago, and it's fantastic. And so the part of the idea here was you can see a short wavelength channel we call Module A, Module B, the two halves of Nearcam. And then the long wavelength channel is, because it's split off with the dichroic, you can see that it's looking at exactly the same piece of sky. So we see two pieces of sky at two wavelengths all the time. And you can pick one filter from over here and one filter from over here. There's some fairly standard combinations that we use so that the exposure times are roughly comparable. And this scheme has worked out very well in practice. So let's go back to the folding up part, because that For a lot of the 6 months of commissioning that took place from early January until the end of June, lining up the telescope was a lot of the deal. And some of that was simply brought about because of the need to fold up things. So this is an Ariane 5 nose cone, and you can see, oh, yeah, it doesn't fit, forget it. This isn't going to work. However, you can fold it up, and then it works. And so a lot of engineering went into how to fold this up, and even more engineering went into testing this segmented mirror and how to control it. And our last cryogenic test, which was the only one with the full telescope and the instrument package. The instrument package is down underneath here, and the collection of equipment up here was designed to inject star-like sources. There are interferometers. There was a photogrammetry system to kind of give a ground truth of where everything was. Very elaborate test. And this chamber is gigantic. You can see from the size of the people. And it was not built for us. We had to spend a lot of money refurbishing it. It was built to test the lunar rover. So talk about repurposing. And it took a lot of cryocoolers and cryogens to keep it cold. And we kept it down at 40 Kelvin for over 90 days. And one of the interesting parts of this test occurred partway in when Hurricane Harvey hit Houston. I happened to be there then, and we kept testing. The telescope was perfectly safe inside this gigantic, thick-walled vacuum chamber. But us people, that was another story. We tried to carpool, and no one got hurt or anything. But it was a little unpleasant for a while because restaurants and grocery stores were closed. And so the project people had to do a little bit of a fast dance to keep us fed. Oops, let's go back one. So we got that cryogenic test was both a lot of fun and somewhat stressful because we had to get it done in a certain amount of time. So this shows the telescope partly folded up at Northrop Grumman in their facility a little ways south of LAX. And this is where the telescope got mated to the sun shield because the sun shield was not part of the test in Houston. The chamber was not big enough to include it. And you can just barely kind of see some cables and things hanging down here. Some of the plumbing for the cryocooler had to go up between these because the compressor for the cryocooler is on the bottom side in the spacecraft. Underneath the sun shield is where the spacecraft is and all of the ground communications and pointing systems live. And of course, we have to get the data off the instruments, which are on the back side of this, down through there. And so getting this connected up was, I don't like cables because they always break, but these guys did it fine. Yoo-hoo. There, oops. Oh my goodness, it stacked them up. Maybe we'll go back and do this by hand. Here we go. Okay. And so this shows it folded up, ready to go into its special shipping container. We had a shipping container that looked a lot like a Quonset hut, but it was basically a portable clean room. So the temperature and air filtration systems traveled with the telescope, and it got loaded into the container, which then got put on a boat at Long Beach and went down the coast of the U.S. and Mexico through the Panama Canal and around to the northeast corner of South America to the European Space Agency's flight facility in French Guiana. And there was a lot of secrecy about this because somebody was worried about pirates and whatever, but it is a valuable payload, cargo. So once we got launched and into space, the next thing we had to do was commission the telescope and instruments, meaning we had to go from where they got into space at basically room temperature, and they cooled down because we deployed the sun shield, And there were 3 phases of this commissioning. The first part I've already mentioned, launch, course corrections to get us right to L2 and the deployments. And then phase 2, which I'll describe in more detail momentarily, was to get those 18 mirror segments to act like a single monolithic mirror. And that was a very choreographed procedure that had been tested out and took quite a bit of effort. And then we had to check out the 4 instruments and make certain that all of them were working correctly, and there are some calibrations that had to be done along the way. And once all of that was done, then we could turn it over to Space Telescope Science Institute to start executing observing programs for the general astronomical community. So there were 6 months allocated for commissioning, and in typical NASA fashion, there are lots of acronyms here. And this green part was where we spent a lot of time getting the telescope aligned properly, and then the instrument checkout happened over here. Nearcam turned on relatively early in this process because it was used in all of this commissioning. And in fact, Nearcam was turned on when the detectors were still at 100 degrees Kelvin. Only the short wavelength detectors would really function at that high a temperature. But the idea was we could find the images from each of the 18 segments at that warm a temperature, because we could pick a very bright star, and so each of the 18 images were quite bright and not too hard to find. And the telescope alignment process had many steps, but there were some that got skipped in the end, like this MIMF stands for multi-instrument, multifield, which was a process designed to make certain that we didn't come into some kind of ambiguous state where there was a tilt of the secondary that was compensated by a tilt of the primary or something of that sort. And we went to quite a bit of length to make certain we didn't do that. But it turned out after the first one, we were good enough. And I will show you what some of these different steps are. You know, finding the stars initially, course phasing was a very important part, and then the fine phasing that led into this other multi-instrument, multi-field part was again important. So this shows you in sort of a graphic format what the general alignment procedure was like. First, we had to find where all the 18 segments are pointing, because launch vibration meant they were somewhat higgledy-piggledy in terms of their tilts. So we had to find these. Then the next step was to do motions of the secondary mirror to get it set to the best average for the 18 segments. Then you had to identify which segment was who, so that when you sent commands to a segment to say change its tilt, you were changing the one you thought you were changing. And then there was a sort of a global alignment step where everything was spaced out very carefully. And then these were stacked. After they were stacked, this image looks a little bit like a star, but it's not yet phased, and so it's not really the end we want. And we did a coarse phasing step and then fine phasing, and this fine phasing part is what's done routinely. And the coarse phasing was done using this dispersed Hartman sensor. Nearcam has 2 of them, and you can see there's some purple rectangles vertical here and 60 degrees here. And I'll show you how those work, but they basically sense the step function between adjacent segments. And the idea of how to do this and the design of the device was the result of work by Paul Atchison, who was an OPSI alum. And as I mentioned, we had to do this multi-instrument, multi-field data before going into the routine wavefront sensing. So the first step is find the segments. And engineers made estimates of how much the mirror segments might be tilted once we got on orbit. And the worst case was that things might be spread out over an area as big as the full moon. So the way to think of this is that when we first started, it was like a telescope comprised of 18 separate telescopes, each mirror segment acting like a small telescope. And there was a pattern laid out. These blue areas correspond to side-by-side Nearcam fields of view that were stepped all around that area to try to find all of the 18 images. But bingo, they were found in a very small area. And that was the first clue, really, that things were going to go a little bit better than the worst case that the engineers predicted. And so once we found them, we had to identify them. And if you count, you'll see that there are 18 of them. And it's very hard to read, but there's little identifying names for them. And you'll see that there's an A set, a B set, and a C set because there are 3 separate prescriptions for the segments depending on where they are in the focal plane, in the primary mirror layout. And in a lot of this process, the pupil imaging lens in Nearcam, which flicks into the short wavelength arm up here, was very helpful. And in fact, this particular image was taken when the mirrors were still higgledy-piggledy, and the segment that's lit up is the one that the telescope was actually pointing at the time. And the wavefront sensing team went, geez, we could just use this to find out which segment was which instead of going through this elaborate tweak procedure. But anyway, and then another key thing was, and this is a really yucky-looking image, but it was overexposed so that you could see the outer edge of pupils inside Nearcam and then make certain that the telescope pupil was lined up with that. So you could think of this as the first step in the global alignment where we've got the 18 segments now in particular locations. You can notice that there are a couple where the focus looks not so good. And if you actually examined these closely, you'd find that most of them have some kind of astigmatism because that's what you get when you have tilt. And when the wavefront sensing guys went through all of this, they were very relieved because they didn't see any aberrations but what could be fixed with the control system on the segments. So that made them feel much better. And here, this little movie goes from that initial state to what was the result of tweaking each of the segments to get the segment as best one could. And so that proceeded. And after that, those 18 images were stacked on top of each other. And if you look closely, you can see interference fringes, because when these are stacked on top of each other, the stacking was so good that the light from different segments was interfering with each other. And of course, that's part of what makes the telescope work good in the end, but we wanted it phased up so that the interference was the way we wanted it, not this kind of interference. And so the way coarse phasing works with this dispersed Hartman sensor is that you can think of segments being displaced by a small amount, and if you put into the beam a disperser, you can get an interference pattern on the detector, and that's exactly what the dispersed Hartman sensor does. This shows you from this old Dave Redding paper just what these sine waves and things look like. And so in actual practice, this is what one of the dispersed Hartman sensors look like. It has 10 grisms, and each has a wedge so that the spectrum produced by overlying 2 segments comes out at a separate place on the Nearcam detector. And if you look, you can see what kind of looks like a barber pole, and it's the frequency of the interference along here that tells you what the step size is. And here is the JWST pupil, and you can see the 0-degree dispersed Hartman sensor, and we had lined it up so only 2 segments contribute to the light, and then you can see the 60-degree ones, only 2 segments contribute to the light. And if you trace all of this around and measure all of these, you can figure out how to adjust the focus setting of each of, the the focus setting of each of these segments, and this is all calibrated by having these spectra taken through a notch filter that gives you a wavelength calibration. And then once we got that coarse phasing done, then the fine phasing is done using focus diverse wavefront sensing, and this just steps through the images doing that. And these images are produced by putting weak lenses that are located in the Nearcam pupil wheel into the beam. So we're not moving the secondary all the time, but we're just rotating the Nearcam pupil wheel, much less intrusive than moving the whole secondary. And by analyzing these images, you can figure out what you need to do the final tweaking up of the image. And the algorithms are explained, and I think they're very closely related to what are used in adaptive optics on the ground, except that we do this every 2 weeks instead of every 2 milliseconds. And then this was the final result, the evaluation image with the alignment really perfect. And you'll notice a few little interesting things in the background. I mean, this was a bright star chosen just because it was bright and isolated. And so it was a convenient target to check the alignment that we had achieved this good state. But if you looked in the background, one of the wavefront sensing guys got tired of looking at stars, and he took the background, went through the background of that alignment image and found all of these galaxies. And if you look at them, you see that the spatial resolution is just amazing. And it's amazing because the telescope was supposed to be diffraction limited at 2 microns. But if you look at these full width half maxima and compare that to the 1.22 lambda over d, you quickly learn that Nearcam plus JWST are diffraction limited at twice the level we could have expected. We're good at 1 micron. And some of the spread at these shorter wavelengths in the measured full width half max in a series of images is because with a pixel scale chosen to sample a 2 micron area disk correctly, you're undersampled at these shortest wavelengths. And so we could have done better if we could have had twice as many detectors. No, not allowed, but anyhow. So the optical performance at the end of that first exercise was just stunning. Now, we did have one little piece of bad luck in May when a micrometeoroid hit the mirror. You can see a little dent here. You can also see that the pupil imaging lens produces a somewhat aberrated image. But what is interesting about this is that you can tell that it happened in the wavefront error. But, the original requirement was to have a wavefront error of less than or equal to 150 nanometers. That initial alignment resulted in 50 nanometers. Just, we could hardly believe that we'd done so well. And after this hit, and after adjusting this segment a little bit to minimize the impact of the hit, the overall wavefront error had only gotten to 60 nanometers, which is still far better than we had expected. And so the image quality, yes, it got degraded a little bit by this micrometeoroid, but not in a way that it's hard to complain when you're already so much better than you were supposed to be. So with that, we could start science. And probably all of you have seen some of these early release images, and I'll talk about some of the what you see in these images in just a moment. This plot is one from the Canadian NIRCam instrument, and you can't read the axes, but this is wavelength, and this is amount of starlight absorbed. And what this is showing is that this particular exoplanet, which passed between, it's orbiting its parent star, and when it's in front of the star, it absorbs the starlight, and you can see water very straightforwardly. People had struggled for years to try to see water using Hubble, and here, blink, hardly any time at all, and we had it. There were some solar system targets done. This picture of Neptune with its rings is the best picture of Neptune and rings that we've ever gotten. And you can see some of its little friends. So why did we go to all this effort to build this telescope? One of the reasons was to try to find the first galaxies to form after the Big Bang. And I've got data on our server over in Steward that's going to show just how close we're getting, and it's pretty close. And this is a teaser. This was the image, this is the JWST, and that's the Hubble. And that's the image that Biden showed, which made a lot of people at NASA really happy to think that their president was that interested. But I want you to notice, for example, here is a galaxy that does not show up in the Hubble image, and yet is very, looks red. It's very prominent in the Webb image, and we're finding lots of those. And so there's much more going on in the red obscured by dust universe than we thought. And this particular image is of a galaxy cluster, and you can see something that astronomers like to study because it lets them see faint things in the background. These arcs are due to gravitational lensing by this massive galaxy cluster, so it's kind of like nature's lens. And not to be outdone, NIRCam was targeted at a few of these galaxies in this image that were known from Hubble, but not understood what their nature was. And these are sort of schematic spectra, and this pair of red and blue lines are a line from ionized hydrogen and oxygen 3, and you can see as the redshift increases down, you can see how those lines go across. And these spectra were taken all at once using this multi-object spectrometer. Very, very nice, efficient way to do things. And I can't help but show a little bit from my own data set, which is still somewhat embargoed because we're writing the papers. But this is part of the deep field is observed by Hubble. And here's a sample distant galaxy. There's that galaxy magnified. And you can see right away that Webb has much better image resolution. And we can see little star-forming clumps in this galaxy, for example. And it's going to take us years to get through all of these data and understand all the consequences. But this is why we built the telescope. And to give you a sense of just exactly how this works, this is an image where you see dust lanes, that kind of dark stuff here. Dust lanes in the galaxy is seen from Hubble. If we go 4 times longer wavelength with Nearcam, that changes quite a bit. And you can, if you look hard, you can just see that this image looks speckled. We're actually resolving that galaxy into stars. And this galaxy is quite a bit further away than we thought we could split it into the individual stars, but it's because the optical performance is so good. And if we go another 4 times longer wavelength, here you see what the mid-infrared instrument sees, and that same galaxy looks totally different. Because in the mid-infrared, you're seeing the dust heated up by the young, hot stars. And so in a way, if you pick your wavelengths and go through the suite of instruments, it's almost like doing a kind of astronomical tomography, seeing the different components that make up that galaxy. And this is another just nice picture showing how having a big telescope, cold in space, really changes the game for mid-infrared astronomers. So this image is from the Spitzer Space Telescope, and the primary mirror of Spitzer was smaller than 1 JWST mirror segment. Spitzer was cooled, the telescope was cooled with liquid helium, and the telescope mirror was typically operated at around 5 degrees Kelvin, so it was very cold, but it was very small, 85 centimeters. And here, we're not quite as cold. The mirror's up at 40 Kelvin, but it's so much bigger that you can now, at this same basic 8 micron wavelength, you can see all kinds of detail that you really couldn't be sure what you were seeing in the upper image. And it's going to be a little while before astronomers adjust to having this kind of capability. And another big research area for Webb is studying exoplanets. And this is a picture from the Large Binocular Telescope. This is where a coronagraph blotted out the bright parent star, which is a naked eye star. And you can see some planets. And we will be studying those planets with Webb. I think some of the observations may be scheduled actually for this next week. And what we would eventually like to be able to do is produce a spectrum that looks like this, like an Earth-like planet. It's an ambitious goal, because the way we will do this is by transits. And so when an exoplanet, here is, you can see kind of orbiting around its parent star, but when the exoplanet goes in front of its star, we see a dip in the light because the planet blocks out some of the starlight. And if you take spectra of the star and take spectra with the exoplanet in front of the star, difference them, you can find out what effect the exoplanet atmosphere is having on the starlight, and that lets you produce a spectrum that tells you what is in the atmosphere. And the reason it's hard to do this for an Earth-like planet is that you can see this shows the size of the sun and the size of Venus, which is basically the same as the size of the Earth. This isn't blocking out a very big fraction of the sun's light, and so you hear the exoplanet transit groups talking about measuring things in parts per million, and that requires a very stable telescope. And one of the things where Webb is again doing great is that it's very stable, partly because it's in space and it's cold, and it's been very much easier to reduce these kind of transit data to look for atmospheres. It took people several years to figure out how to do this very well with Hubble, and Hubble is actually a very bad platform for this kind of work because it's an orbit around the Earth, and so you can only take data continuously on average for about 50 minutes, and then you have to kind of start the whole stabilization process over again. Whereas in principle with Webb you could go for about 10 days. Now typically a transit you only observe for maybe 12 hours, so it's not quite so demanding as going for days. But Webb is proving to be a much better platform than Hubble. And the way Nearcam did this, and we tested it in commissioning, is that we have the two arms split by the beam dichroic, and the short wavelength arm uses one of the weak lenses to form an image. And the reason for using a weak lens to spread out the starlight is that this star would be too bright and would saturate if we just did it in a direct image focused. So we put in the weak lens to spread the light out, but it serves as a good monitor of the throughput and so forth. And in the long wavelength arm, we put in a grism and we get a spectrum. And we observe these two types of images for a number of hours. And the particular transit that we used for our commissioning test, the planet was relatively close to a limb, but not right on the limb. And what we discovered by summing up the light in the spectrum was, why was there a jump? No one expected this jump. This was a little bit of a puzzle. But by looking at the weak lens data in the short wavelength arm, what we discovered was that, this is the normal weak lens image. And if you ratio that as a function of time, what we discovered is that when the jump occurred, there was a spontaneous tilt event of a mirror segment. And those happened relatively often during commissioning and were thought to be due to release of stress induced by the cool down. And whether it was something in the actuators getting some stress relieved or something in other materials. We still don't know, but they've almost stopped. But it was somewhat fortuitous that we had this weak lens data that made it very clear what was going on. I have to say that the particular exoplanet chosen for this observation was one that nobody else was interested in. It has a gray spectrum, and it was great for determining what the noise level was, but not particularly scientifically interesting. What was more interesting was an observation released quite recently by one of the early release science teams. And what you're seeing here again is a plot of amount of light absorbed versus wavelength, and the center here is at 4.3 microns. And at long last, astronomers detected carbon dioxide on an exoplanet. So we now have greenhouse gases on exoplanets, and whether or not climate change on exoplanets will become a research area, your guess is as good as mine, but at least we have the tools. And of course, this is the Goldilocks for the Holy Grail for exoplanet astronomers. And this is what they would get across the whole wavelength range of Webb if we can detect the spectrum from an Earth-like planet. And there are plans to try. So the long and the short of it is JWST is working fabulously. There are going to still be more image releases as we go along. My own team, I hope, will have a release about finding some of the most distant galaxies in a few weeks. And I hope I've given you a little bit of a sense of what it was like to line up this telescope. Thank you.
Is there anything you would do differently based on what you know now?
Yeah, there are a few things I would do differently. The first thing I would do is that the fine guidance sensor uses the same kind of arrays as you find in Nearcam, 2K by 2K Merket telluride. And they were worried about having enough sensitivity. They had a requirement of being able to observe a certain brightness star anywhere on the sky in 16 milliseconds. And they decided that they would use a long wavelength cutoff array because they got a little bit more spectral range from the 2.5 to 5 micron region. Stars actually aren't very bright there, and it turns out that the long wavelength arrays have many more bad pixels. And it would have been better to use a short wavelength array, particularly because we discovered the throughput of the whole system's a little bit better than we predicted. And there are sometimes still now even some guide star acquisition failures because they try to guide on a bad pixel, which doesn't work very well. So that would be the first thing I would do, for sure.
Wasn't there another accident where the sunshade was damaged?
No, the sunshade is okay. It was only, that micrometeoroid only hit the mirror. It didn't do, as far as we know, it didn't do anything to the sun shield because the temperatures have been running very steady. So the sun shield has not changed since it was deployed.
What are the chances of meteor or micrometeor hitting the sunshade, and what would happen if that's the case?
That was something worried about quite a bit. And there's a whole group at Marshall Space Flight Center that worries about what kind of debris there is in the solar system. And the hits on the mirror where we can get a detection are running about once a month, which was the rate they predicted. The way the sun shield has been handled, you can't see in the images that I showed, but each layer of the sun shield was constructed as sort of squares that were hot welded together. And so if a micrometeoroid hits something on the sun shield, the damage won't propagate very far. And so there undoubtedly have been some hits, and there was a budget for how degraded the sun shield might be at the end of mission. And so far that looks okay.
Any other questions?
What was the part of the Nearcam that kind of kept you up at night before commissioning?
Oh.
Or, I mean,
before we got it turned on and saw light through it, when we were testing Nearcam at Lockheed and then at Goddard and then at Houston, we discovered that in the module B, the short wavelength channel bore sight kept shifting of 10 pixels one way or the other. And it turned out each of these test sites, we were in a different orientation relative to gravity. And we finally figured out that there is a fold mirror in the short wavelength arm that apparently one of the three struts holding it to the mirror mount must have come unglued from the mirror. And there was quite a bit of effort put into mechanical modeling to be sure that that would survive the launch vibrations with only two struts still attached. And so I kept having these nightmares that we'd only have a one module Nearcam, but turns out no problem. We got on orbit, and the beauty of the lens mount, the mirror mount design, was that once it got fully cold, the outer band clamped down and it can't move anymore now as long as it stays cold. But until I saw that it hadn't gone completely haywire, I was a little nervous.